The National Electrical Code, or NEC, specifies clearance distances for bus plugs. For top-mounted bus plugs, 42 inches of clear space above the plug is typically required, according to NEC section 430.10 burn. For bottom-mounted bus plugs, 30 inches of clear space below the plug is generally required, as per NEC section 430.10b2. However, there are exceptions for top-mounted bus plugs. One exception allows for a reduced clearance of 30 inches above the plug if an overcurrent device is located at or within 12 inches of the bus plug. This is detailed in NEC section 430.10c. Another exception allows for a reduced clearance of 30 inches if the bus plug is separated from all other conductive objects by a distance of at least 12 inches, also according to NEC section 430.10c. The NEC does not specifically address clearance distances for 400 amp and 600 amp bus plugs. However, it is generally recommended to follow the same clearance requirements as for 2000 amp bus plugs. That means 42 inches for top-mounted plugs and 30 inches for bottom-mounted plugs. When evaluating bus plug clearances, it's important to consider potential hazards, even if the plugs do not require frequent maintenance. Insufficient clearance can increase the risk of arc flash if a fault occurs on the bus or the plug. Obstructions within the clearance zone can make it difficult to access and service the plug if necessary. Adequate clearance is essential to ensure the safety of personnel working near or on the bus. To summarize, it's recommended to adhere to the 42-inch clearance requirement for top-mounted 2000 amp bus plugs. For other bus plugs, the clearance distances should be determined based on the specific hazards and the requirements of the local electrical code. It is important to ensure electrical safety when working with or near bus plugs. Firstly, always to energize the equipment before working on it unless live work is specifically permitted and proper precautions are in place. Secondly, use appropriate personal protective equipment, or PPE, such as arc-rated clothing, gloves, and face shields. Thirdly, maintain a safe working distance from energized equipment. Fourthly, be aware of the potential hazards, such as arc flash and electrical shock. Fifthly, follow lockout-tagout procedures to prevent accidental energization. Sixthly, inspect equipment regularly for signs of damage or wear. Seventhly, ensure proper ventilation to prevent the buildup of hazardous gases. Eighthly, use insulated tools and equipment. Ninthly, provide adequate lighting for the work area. Tenthly, train personnel on proper safety procedures. Arc flash is a dangerous phenomenon that can occur when electrical current flows through the air between conductors. The heat from an arc flash can reach extremely high temperatures, causing severe burns, explosions, and fires. Arc flash can also damage equipment and disrupt power supply. Several factors can contribute to the occurrence of arc flash, including insulation failure, accidental contact with energized parts, and equipment malfunction. To mitigate the risk of arc flash, it is essential to implement safety measures such as using arc-rated PPE, maintaining safe working distances, and installing arc flash protection devices. Electrical shock occurs when a person comes into contact with an energized electrical conductor. The severity of an electrical shock depends on several factors, including the voltage, the current, and the duration of contact. Electrical shock can cause a range of injuries, from mild tingling to cardiac arrest and death. To prevent electrical shock, it is important to use insulated tools and equipment, maintain proper grounding, and avoid contact with energized parts. Electrical codes, such as the NEC, provide guidelines for the safe installation and operation of electrical systems. These codes specify requirements for wiring, grounding, overcurrent protection, and other safety measures. Adhering to electrical codes is essential to prevent electrical hazards and ensure the safety of personnel and equipment. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current to flow. Grounding helps to prevent electrical shock and minimize the risk of fire. Proper grounding requires the use of grounding conductors, grounding electrodes, and bonding techniques. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect electrical circuits from excessive current. Overcurrent protection devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. Regular inspection and maintenance of electrical equipment are essential to identify and correct potential hazards. Inspection should include visual checks for damage, testing of insulation resistance, and verification of proper grounding. Maintenance should include cleaning, lubrication, and replacement of worn or damaged parts. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. Training is essential to ensure that personnel are knowledgeable about electrical hazards and safety procedures. Training should cover topics such as arc flash awareness, electrical shock prevention, grounding, and lockout-tagout. Insulation is used to prevent electrical current from flowing through unintended paths. Insulation is typically made of materials such as rubber, plastic, or ceramic. Damaged or deteriorated insulation can create a shock hazard and should be repaired or replaced. Bonding is the process of connecting metallic parts of an electrical system together to create a low-impedance path for fault current. Bonding helps to prevent electrical shock and minimize the risk of fire. A qualified electrician is a person who has the knowledge, skills, and experience to safely install, maintain, and repair electrical systems. It is important to use a qualified electrician for all electrical work to ensure that it is done safely and in accordance with electrical codes. Electrical safety audits are conducted to identify potential electrical hazards and assess the effectiveness of safety measures. Audits should be conducted by qualified personnel and should include a review of electrical systems, equipment, and procedures. Electrical safety programs are comprehensive plans that outline the policies, procedures, and training required to prevent electrical hazards. Electrical safety programs should be tailored to the specific needs of the workplace and should be regularly reviewed and updated. Before working on any electrical equipment, it is essential to identify all potential hazards. This includes identifying energized parts, potential sources of arc flash, and other potential hazards. A job safety analysis, or JSA, is a systematic process for identifying and evaluating potential hazards associated with a specific task. A JSA should be completed before starting any electrical work to ensure that all hazards are identified and mitigated. A hot work permit is required for any work that involves the potential for arc flash or electrical shock. The permit should specify the safety precautions that must be taken to prevent these hazards. Personal protective equipment, or PPE, is essential for protecting workers from electrical hazards. PPE should be selected based on the specific hazards present and should be properly maintained and inspected. Arc-rated clothing is designed to protect workers from the heat of an arc flash. Arc-rated clothing is made of materials that are resistant to ignition and will not melt or drip onto the skin. Insulated gloves are designed to protect workers from electrical shock. Insulated gloves are made of rubber or other insulating materials and should be inspected for damage before each use. Face shields are designed to protect workers from arc flash and other hazards. Face shields should be made of materials that are impact resistant and will not melt or drip onto the skin. Safety glasses are designed to protect workers' eyes from flying objects and other hazards. Safety glasses should be worn at all times when working with electrical equipment. Ground fault circuit interrupters, or GFCIs, are designed to protect workers from electrical shock. GFCIs interrupt the flow of current when a ground fault is detected, preventing electrical shock. Extension cords should be used with caution to avoid electrical hazards. Extension cords should be properly grounded and should not be overloaded. Power strips should be used with caution to avoid electrical hazards. Power strips should be properly grounded and should not be overloaded. Surge protectors are designed to protect electrical equipment from voltage surges. Surge protectors should be used to protect sensitive electronic equipment. Portable generators should be used with caution to avoid electrical hazards. Portable generators should be properly grounded and should not be operated in enclosed spaces. When working with electrical equipment, it is important to be aware of the potential for static electricity. Static electricity can cause damage to electronic equipment and can also ignite flammable materials. To prevent static electricity, use anti-static masks, wrist straps, and other anti-static devices. When working with electrical equipment, it is important to be aware of the potential for electromagnetic interference, or EMI. EMI can disrupt the operation of electronic equipment and can also cause inaccurate readings. To prevent EMI, use shielded cables, filters, and other EMI reduction devices. When working with electrical equipment, it is important to be aware of the potential for radio frequency interference, or RFI. RFI can disrupt the operation of electronic equipment and can also cause inaccurate readings. To prevent RFI, use shielded cables, filters, and other RFI reduction devices. When working with electrical equipment, it is important to be aware of the potential for corrosion. Corrosion can damage electrical equipment and can also create a shock hazard. To prevent corrosion, use corrosion-resistant materials, coatings, and other corrosion prevention devices. When working with electrical equipment, it is important to be aware of the potential for vibration. Vibration can damage electrical equipment and can also cause fatigue. To prevent vibration, use vibration isolation mats, dampers, and other vibration reduction devices. When working with electrical equipment, it is important to be aware of the potential for temperature extremes. Temperature extremes can damage electrical equipment and can also cause inaccurate readings. To prevent temperature extremes, use temperature control devices, insulation, and other temperature protection devices. When working with electrical equipment, it is important to be aware of the potential for humidity. Humidity can damage electrical equipment and can also create a shock hazard. To prevent humidity, use dehumidifiers, desiccants, and other humidity-controlled devices. When working with electrical equipment, it is important to be aware of the potential for dust and dirt. Dust and dirt can damage electrical equipment and can also create a fire hazard. To prevent dust and dirt, use filters, enclosures, and other dust and dirt-controlled devices. When working with electrical equipment, it is important to be aware of the potential for rodents and insects. Rodents and insects can damage electrical equipment and can also create a fire hazard. To prevent rodents and insects, use rodent and insect control devices, sealants, and other pest control devices. When working with electrical equipment, it is important to be aware of the potential for flooding. Flooding can damage electrical equipment and can also create a shock hazard. To prevent flooding, use flood barriers, sump pumps, and other flood control devices. When working with electrical equipment, it is important to be aware of the potential for earthquakes. Earthquakes can damage electrical equipment and can also create a fire hazard. To prevent earthquake damage, use earthquake-resistant construction techniques, bracing, and other earthquake protection devices. When working with electrical equipment, it is important to be aware of the potential for high winds. High winds can damage electrical equipment and can also create a fire hazard. To prevent wind damage, use wind-resistant construction techniques, anchoring, and other wind protection devices. When working with electrical equipment, it is important to be aware of the potential for snow and ice. Snow and ice can damage electrical equipment and can also create a shock hazard. To prevent snow and ice damage, use snow and ice removal techniques, de-icing equipment, and other snow and ice protection devices. Remember to consult the NEC and local electrical codes for specific requirements and regulations. These codes provide detailed information on safe electrical practices and are essential for ensuring the safety of personnel and equipment. For example, NEC Article 250 covers grounding and bonding requirements, while NEC Article 310 covers conductor ampacity. Understanding and adhering to these codes is crucial for preventing electrical hazards. Always prioritize safety and seek guidance from qualified professionals when working with electrical systems.